Hello, and welcome to this explainer. I am absolutely thrilled to have you here today. The term Internet of Things, or IoT, gets thrown around literally all the time. Tech news, business meetings, even commercials for refrigerators. But today, we are moving way past the buzzwords. Our goal is to completely demystify the foundational mechanics of IoT. We're going to break down exactly how these massive systems are built, how they operate in the real world, and the invisible rules that govern them.
Okay, let's dive right into this. Think about this for a second. What exactly connects a rural farm measuring soil moisture, a massive smart city managing its traffic lights, and that little smart thermostat sitting right there in your hallway? Well, the answer isn't just the internet. It's actually a highly complex, deeply layered architecture of sensors, edge computers, and communication protocols. It's essentially a vast, interconnected physical world talking directly to a digital one.
To really understand how the whole shebang works, we need a structured approach. So today's explainer is rooted directly in this comprehensive academic syllabus, and we're zeroing in specifically on Chapter 1. We're going to rigorously explore the core concepts, the real importance of these systems, their interdisciplinary applications, the very real technical challenges they face out in the wild, and finally, the standards that hold it all together.
Here is our roadmap for today. Number 1, core concepts. Number 2, why IoT matters. 3, industries and applications. 4, key challenges. And 5, the role of standards.
All right, starting things off with Section 1, core concepts of IoT. So what actually is it? The Internet of Things is an internet-integrated, scalable architecture that bridges physical devices to digital networks for data collection and control. Now, the absolutely crucial word there is scalable. For IoT to work on a global scale, we aren't just talking about a few thousand devices. We are talking about billions. Billions. And because of this massive scalability demand, the old Internet addressing system, IPv4, well, it just isn't enough anymore. Actually, transitioning to the vast address space of IPv6 is completely mandatory for IoT to function. Every single tiny sensor needs its own unique identity.
Now, what's really interesting here is the contrast between the past and the present. Traditionally, we had machine-to-machine or M-to-M communication, which was highly localized and isolated. Think of, say, a factory machine talking only to a computer on that exact same factory floor. But modern IoT changes the paradigm entirely. It's a fully internet-integrated architecture. It takes those isolated, localized connections and opens them up to massive scalability, allowing everyday devices to integrate seamlessly with global networks and cloud intelligence.
Moving right along to Section 2. Why IoT matters. Traditionally, a company sold a physical product, let's say a jet engine or an RFID tracking system, as a one-and-done transaction. You buy it, you own it. But IoT enables a massive fundamental shift toward product as a service, or PaaS. Because the product is continuously connected, companies can now provide service-oriented value. It's kind of like renting software in the cloud instead of buying a physical disk, right? You don't necessarily buy the jet engine, you pay for the hours it actively runs. And to make this work seamlessly, businesses rely heavily on underlying structural elements, like the EPC Global Network Framework, to successfully integrate complex billing capabilities across these massive connected networks.
Next up, Section 3, industries and interdisciplinary applications.
Notice the massive difference between these two everyday use cases. In smart logistics, you're tracking fleets of moving trucks. The mobility demand is incredibly high, right? Which means the network requires dynamic addressing schemes just to manage connectivity as these devices rapidly move across different network boundaries. Now compare that to environmental monitoring for something like forest fires. Those sensor arrays are entirely stationary. They just sit there. So the architectural focus completely shifts from tracking fast movement to ensuring ultra-reliable data collection from fixed, often very remote locations. Now imagine scaling that up to a massive smart city project like Hansa Technopolis. A single smart city contains vastly different technological demands all running at once. You have general urban infrastructure, things like smart parking or structural health monitoring for bridges. These absolutely need to be reliable, but, they can handle slightly lower latency networks. A small delay isn't the end of the world. But then you have emergency response systems. These are mission critical. They demand ultra-low latency because they are quite literally life-saving. The overarching IoT architecture has to perfectly accommodate both of these extreme demands simultaneously.
Which brings us to Section 4, the reality check, key IoT challenges.
And this brilliantly illustrates one of the biggest hurdles, getting data where it needs to go without losing it. Look at this experimental data.
When sending data all the way to centralized cloud servers, packet loss hits roughly 4.8%, and throughput drops. But when we use edge computing, meaning we process the data locally, much closer to the actual sensor, packet loss drops dramatically to just 1.6%, and throughput increases. So when you're dealing with time-sensitive tasks, relying solely on the cloud is, frankly, often a major liability.
We actually see this exact dynamic play out in smart agriculture. If a rural farm uses pure cloud computing, the constant transmission of raw data causes high latency, eats up precious bandwidth, and completely drains sensor batteries. And let's be real, absolutely nobody wants to drive a tractor miles out into a muddy field just to change a battery. Edge computing solves this beautifully. By locally filtering the data right there on the farm, it provides low latency and crucial operational resilience. And most importantly, it saves vital battery power by reducing communication overhead, even when you factor in the energy cost of processing that data locally.
But, as with literally everything in tech, there are always trade-offs, especially regarding security. Processing sensitive data locally at the edge is fantastic for data privacy. It minimizes exposure to public network breaches and central cloud vulnerabilities. However, because these edge gateways and sensors are physically deployed out in the open, in exposed rural or industrial locations, they face unique physical tampering risks. You might perfectly secure the network from hackers, but someone could literally walk right up and smash or tamper with the physical hardware.
Finally, we arrive at Section 5, the role of standards.
Let me tell you, interoperability is a massive headache for IoT developers right now. We essentially have this giant alphabet soup of standards organizations: IEEE, IETF, the W3C. Honestly, it's enough to make an engineer dizzy. Now, all of them are doing vital, important work. But the coexistence of these multiple bodies, each with slightly different priorities, creates overlapping standards. And this leads directly to ecosystem fragmentation, making it incredibly difficult to get different smart devices to just seamlessly talk to each other. Let's break down two of the most critical communication acronyms you'll definitely encounter. First is MQTT. This uses a publish-subscribe broker architecture. What it does is beautifully decouple the sender from the receiver, making it completely ideal for unreliable, heavy-duty industrial networks. Second is CoAP. Now, this is an HTTP-like request-response model. It's much more lightweight, making it the absolute perfect standard for highly resource-constrained sensor networks. Knowing exactly which protocol to use is honestly half the battle.
Beyond just how devices talk, we also have to standardize how far their signals actually reach, because different standards serve entirely different scales. Protocols like Zigbee and Z-Wave are incredibly effective for localized home automation, like connecting your smart light bulbs to your hub in the living room. But if you want to connect a massive city's water meters, well, you need LPWAN technologies like LoRaWAN. These are explicitly designed for long-range, low-power, large-scale deployments.
So, the crucial point is this. With all this fragmentation, different protocols, different ranges, different hardware platforms, how does an entire IoT system actually function without falling apart? Well, the unsung heroes here are middleware and edge gateways. They serve as absolutely critical abstraction layers, decoupling the application logic from the underlying hardware. If a sensor speaks CoAP and a server expects MQTT, these decentralized edge frameworks translate those incompatible data formats locally, right on the spot, without ever needing to bounce the data all the way to a cloud intermediary.
And that brings us to our final thought. We've seen how IPv6 is actively allowing billions of new devices to connect globally, essentially creating a massive, decentralized physical web. But the true next frontier? It's security and interoperability. As this expands, how will emerging technologies ultimately secure our massively interconnected physical world? Well, we are already seeing blockchain being used to eliminate centralized single points of failure by providing decentralized identity management. We're seeing AI optimizing those blockchains and edge-based federated learning models allowing for advanced analytics that still preserve strict data privacy. The basic mechanics of IoT are firmly in place, but the evolution of how we secure this massively interconnected world is really just beginning. Thank you so much for joining me for this explainer. I really hope it helped clarify the complex, amazing architecture bringing our physical world online.